All right, so then step 3, let's pick back up here and actually solve this eigenproblem. In the x direction, we have d squared theta x dx squared plus lambda squared theta x to get our c1 sine plus c1 or c2 cosine. If that's the solution to that particular ODE. So now our task is to go through and start enforcing the boundary conditions to solve the eigenproblem. So let's restate what we have here. So we have theta at x equals 0 is equal to 0. That was one boundary condition. The other boundary condition was minus k partial of theta with respect to x at x equals w is equal to h bar theta at x equals w. Those were our two boundary conditions that we're dealing with. Right, what was the step here that we had to do? We're saying theta is a function of x and y. We're only concerning ourselves now with the x part of this problem. So we actually need to sub back in our assumption that theta x times theta y is the true form of theta and restate these boundary conditions as needed. So we'll say theta x at x equals 0 times theta y has to be 0, right? That's just restating that boundary condition based on our assumption. We have theta x times theta y. Theta y is not changing as a function of position x, right? Theta y is a single function only in terms of y. So when we're looking at just the x part of the boundary condition, that can divide out. It's effectively a constant that we can divide out. So we end up with theta x at x equals 0 is equal to 0. Okay, so that's seems trivial, but it's our restatement of this boundary condition in terms of our assumption theta x times theta y is the form that we're going for. Okay, so that was the first boundary condition over here. This is 1. For 2, we have to restate this on that same assumption. It's kind of an equally simple thing to do, but we say minus k. So we have now theta x times theta y. Theta y is a constant, so it becomes theta y times the partial of theta x with respect to x at x equals w is equal to h bar times theta x times theta y. So theta x is at x equals w. So now on both sides of this equation, we have theta y, which again is not changing as a function of position x. So this can cancel out of this equation. Okay, and then our restated boundary condition is just minus k d. Right now, the normal differential operator, no longer partial, d theta x dx at x equals w is equal to h bar times theta x at x equals w. Right, so those are our two x direction boundary conditions that we've now restated in terms of theta. Questions on that? Okay, I mean it's like a lot of words to basically just tack an x on in the subscript. Okay, but for the problems we're doing, that's basically all we have to do here. I think there's other situations where that's not the case, so we just kind of are pedantic about it. Okay, so now let's make myself some room over here. So let's go through and actually solve to try to get the eigencondition here. We're going to enforce the boundary conditions first. We're going to say theta x at x equals 0 equals 0. So let's enforce this boundary condition on our temperature solution or our theta solution, right? So theta x at x equals 0 is equal to c1 sine of lambda times 0, it's x equals 0, plus c2 times cosine of lambda times 0. Right, and that all has to equal 0. 0 is equal to that. All right, so let's see. This evaluates to 1. This evaluates to 0. So we're saying here c2 is equal to 0. Okay. So then we're left with our expression theta x is equal to c1 times sine of x. That's what we can move forward with here. Okay, second boundary condition. We're going to say minus k times d theta x dx evaluated at x equals w is equal to h bar theta x at x equals w. So now let's, so evaluate the derivative, right? So the derivative now of theta x is, what's the derivative of sine of x? Well, it's just, oops, sorry, I missed a lambda up there, didn't I? So, sorry, theta x is sine lambda times x. Sorry about that. So what's the derivative of that function? It's just cosine, or lambda times cosine. Okay, so we end up with, here we have minus k times lambda times c1 times cosine of lambda w, right? We're evaluating this at w, is equal to h bar times c1 times, what is my theta function? Is just sine lambda w. Okay, so now we have eliminated the x from this equation, and we're left with something where we can solve directly for c1. Okay, we solve this out, and we end up with the eigencondition. So actually c1 goes away, and we end up with minus k times lambda over h bar, I should bring the h bar over, is equal to sine over cosine less tan of lambda times w. Okay, so this thing here, right, this is, we enforce the boundary conditions to be able to figure out what the lambda values are going to be, our eigenvalues. So this is our eigencondition. Eigencondition is the equation that you need to satisfy infinitely many times to get your lambda values out of it. If you remember last time or the previous times we've solved these problems, what we've had is an eigencondition where you can kind of look at that problem and you can see that for certain values, it would say like, pi over 2 or 3 pi over 2 or whatever, that you can kind of by inspection see where that problem is true or where that statement is true. Here now we have lambdas on the left-hand side, but then we also have lambda in the argument for tan. So we can't explicitly solve for lambda and get a bunch of different eigenvalues. So you have to take a slightly different approach for this in order to figure out what those lambda values are.